Okay, so I want you to get out your periodic table and take a look at sulfur and oxygen. And I want you to come up with a compound that can contain both substances. So pause the video, take a second, and try to draw this structure that will contain both sulfur and oxygen. All right, let's take a look. So using the octet rule, you might think, oh, well, sulfur needs 2 bonds and oxygen needs 2 bonds. So they're just going to double bond to each other and form the SO molecule. But what's interesting about this story is that this is actually not the most likely compound formed by the presence of oxygen and sulfur. And one of the reasons for that is that there's always more oxygens around in the environment than just a 1-to-1 ratio. Because there's more oxygens, those oxygens are kind of like, we want to get in on the action. And so if you had an SO molecule and then an O2 molecule comes along, those oxygens are like, wait, why are we bonded to each other when we can pick on the element with a lower electronegativity? So oxygens will break up with each other because they're pulling on electrons with equal force, and they begin to team up and bully the sulfur. If you take a look at the electronegativity chart, one thing you're going to notice is that oxygen is a lot more electronegative than sulfur. Oxygen sits here at 3.44 and sulfur at 2.58. So these oxygens are going to force sulfur to break up its lone pairs to give electrons to oxygen so that oxygen can form its 2 bonds with something with a lower electronegativity, and that's going to force sulfur to make more than 2 bonds. So let's take a look at an example here of sulfur dioxide. Sulfur dioxide is a common gas given off by volcanic eruptions and the decay of matter in mud and in different environments. So let's take a look. We're going to go ahead and make our chemical bonds. So here you'll notice that sulfur has made 2 bonds, one with each oxygen. Now you'll notice that the oxygens are not yet following the octet rule. The sulfur is 2, 4, 6, 8, but each oxygen is only 2, 4, 6, 7. And there's a rule that says the element with the higher electronegativity must follow the octet rule, and an element with a lower electronegativity can become hypervalent. Now, some of you may be tempted to go straight across here and make a triangle. Do not make a triangle because that is not geometrically possible. The tightest angle that we're going to be able to make is 90 degrees. So we can't make smaller than 90 degrees. So what are we going to do? What we're going to do is we're going to break up one of the lone pairs of the sulfur. One of those lone pairs is going to break up, and now you can see that they've lined up with the unpaired electron from each oxygen. And we've got a double bond for each oxygen. At this stage, sulfur has 10 valence electrons. 2, 4, 6, 8, 10. So we would say because it's greater than 8, it's hypervalent. Another term you might see on the internet is expanded octet. We're going to use hypervalent. So remember that the higher electronegative atom will always fill its octet at the cost of the lower electronegative atom. So this is what the chemical structure of sulfur dioxide would look like. It ends up having 3 directions in space. It double bonds with this oxygen, giving it 8. It double bonds with this oxygen, giving it 8. That lone pair sits up here in the top, and because they're still there and they are repelling electrons, they kind of push these down. So it's not a linear structure, it's a bent structure, because the pair of electrons up here is still pushing the oxygens down at an angle. All right, see if you can draw the sulfur trioxide molecule, SO3. SO3 is formed in the presence when sulfur dioxide is in the presence of oxygen gas at high temperatures, like, for instance, in a volcanic eruption or in the furnace of a coal-burning power plant, where sulfur dioxide is being produced in the burning of coal, and then oxygen from the air reacts with it. What does sulfur trioxide look like? Take a minute, make a drawing, and see if you can figure it out. All right, so you've unmuted or you've unpaused your video. Let's take a look. Another oxygen comes in and breaks up that lone pair that was on the sulfur dioxide and makes 2 more bonds. Now that sulfur is got 6 bonds around it, or 12 valence electrons. So we say it's hypervalent. Each oxygen contains 8 around it. Oxygen gets to follow the octet rule, sulfur doesn't. Okay, now we're going to draw the sulfate polyatomic ion. That is SO4 -2. Now what this means is that you're going to have 4 oxygens attached to the sulfur, but there's a bonus here. The -2 charge indicates that we get to add 2 extra electrons somewhere to make sure everybody's following the octet rule except sulfur. So you get 2 extra electrons to work with. Pause the video, see if you can draw it. Okay, so we're back. Let's take a look. This is the sulfate polyatomic ion. What will happen is that we've got our 2 double bonded oxygens, each oxygen following the octet rule with 8. Sulfur is then going to single bond to the other 2 to make 4 attached to the sulfur. But when that single bond occurs, each oxygen has 7 valence electrons. They are not following the octet rule yet. However, I told you had a bonus of 2 electrons. If you were to add an additional electron to each oxygen, you get to 8. Notice that it will then give it a negative charge. And since we're doing it to 2 oxygens, that becomes -2. So if you add an electron to try to make an element follow the octet rule, that's going to become a negatively charged ion.